Hello and welcome to our solar program in conjunction with Explore UT and the Texas Science Festival. My name is Joe Wheelock, and I'm coming to you live from the McDonald Observatory in far west Texas. Today you will learn many fun things about our nearest star, the Sun, and we'll also show you live solar views. Now I live and work here at McDonald Observatory. I've been here for over 21 years. I've been interested in astronomy since I was a kid. Before I came here, I did work in a planetarium and also public programs for an astronomy club. Now, I have a degree in electronics, and I've also had courses in chemistry, physics, and mathematics, but my real passion has always been astronomy. But now I want to introduce my co-host, Judy Meyer, and she'll be helping out today during the program, and she'll tell you about her role and an overview about the program today. So, Judy?
Well, hi, Joe.
Hello.
I'm really happy to be here. I am Judy Meyer, and I live and work here at McDonald Observatory. I work with visitor programs, I work with K-12 education, and what that means is I work with students and teachers and everyone, including you. And I've been at McDonald Observatory for just a few years less than Joe has. So he's our experienced one, and I'm the younger one. No, not really. Anyway, here's what we're going to do here. We are going to talk about the sun. We're going to start by talking about where we are, and then we'll talk about our telescopes, how to safely view the sun, some things we know about the sun. We'll move over to the live views, and then we'll tie up everything with talking about eclipses, because for those of you in Texas, there's going to be a total solar eclipse that you'll be able to see in just a few years. Now, questions are always welcome, and I like to encourage you to ask questions. We have moderators in the chat who want to answer your questions. We'll try to answer as many as possible. Asking a question is a really great way to learn new things. So don't be shy about asking questions. If there are some questions that the moderators think that we ought to answer, we'll try to get to those near the end of the chat, of the time here. So please ask questions. And now back to you, Joe.
Okay, thank you, Judy. And again, if you have any questions, post them in the chat, and we'll try to get to as many today as possible. Okay, so let's go ahead and get on with our program today. Now, the McDonald Observatory, we are located in far west Texas. We're in the Davis Mountains region. You can see our location here on this map. And here's a picture of some of our telescope domes that we have here at the observatory. In the foreground, you can see two domes. The smaller dome contains our 82-inch or 2.1 meter Otto Struve telescope, opened up in 1939. The dome next to it contains our 107-inch or 2.7 meter Harlan J. Smith telescope, opened up in the late 1960s. In the background, you can see the silver dome of the Hobby Everly telescope. That is one of the largest telescopes in the world. In fact, we'll be doing a virtual tour of that telescope on March the 10th, beginning at 1 o'clock Central Time. So join us for that program if you can. Now, I'm not located at the summit of the mountain. I'm actually located at the base of the mountain. I am located in our old visitor center. And here we can see a video of our complex, our telescope park, and our visitor center. And Judy mentioned about the programs that we're offering right now. And the telescopes we'll be using today, they're located in what is called a roll-off roof observatory. The roof just rolls back and allows us access to the sky. And here are the telescopes we will be using to view the sun today. We have three telescopes. We have a 6-inch or 152 millimeter telescope that allows us to view the sun close up. We also have a couple of smaller telescopes that allow us wide angle views of the sun. We have filters and cameras on the telescope that allows for safe views of the sun. The mounting the telescope is on compensates for the Earth's rotation, tracks an object across the sky, and it is computer controlled. Now, I mentioned that we have filters to view the sun safely at our telescopes. Now, to view the sun safely, you can use a filter that fits on the very end of a telescope or project the image onto a piece of white paper or a piece of white cardboard. And some quick facts about the sun. The sun, it is made up mostly of hydrogen, also helium, and trace amounts of other elements. It has a diameter of 865,000 miles, or 1.4 million kilometers. It's about 93 million miles away from the Earth, or 150 million kilometers. The temperature of the sun is about 10,000 degrees Fahrenheit, or about 5,500 degrees Celsius. Estimated age of the sun is about 4.5 billion years old. Okay, so those are some quick facts here about the sun. Okay, let's go ahead and get on with our live views of the sun here. Get that fired up here for you. Okay, so here we have a live view of the sun, and this is using one of our smaller telescopes. In addition to the image of the sun, we can see the controls that I use for the telescope and also for the cameras. And to prove to you this is not a picture, I will move the telescope. Not moving the sun, moving the telescope. So that is a live view of the sun. The bottom section, the bottom controls are for the cameras, and I'll be making heavy use of those later on during the program. So I mentioned earlier the size of the sun, 865,000 miles, or 1.4 million kilometers. 109 Earths would fit across the disk of the sun. How many Earths do you think might fit inside of the sun? If you know that answer, put it in the chat and we'll answer the question later on. Now you'll notice there isn't much happening on the sun right now. Well, right now the sun is coming out of a deep solar minimum. Once every 11 years, the sun reaches a peak of activity where we have a lot of things happening on the sun. Our next solar maximum will be in about 4 years or so. Now, when I move the telescope, you may have seen a couple of look like specks that are moving at the sun. Those are sunspots. We'll show you some pictures of sunspots in a few minutes, whenever, since we don't have many sunspots visible right now. But I want to turn things over to Judy for just a couple of minutes. She's going to talk to you about how we will view the sun next with our telescopes. So Judy, take it away for just a few minutes here.
Okay. Thank you, Joe. Let me get my slide up there. Where's my slide? There it is. So I want to talk about how we've been looking at the sun. We've been looking at the visible light of the sun. And the visible light just means we're looking at all the light that comes from the sun, and we cut it down to a safe amount. Sometimes we call it the white light view of the sun. And what I have on my slide here is a view of the sun not from today. It's from about 5 years ago. And you can see that in that view, we can see a few sunspots. A few sunspots, those are the dark spots on the sun. But it turns out that we're looking at the overall light of the sun, but if we look at the light in a different way, we can learn about the sun differently. So I want to take sunlight and look at it in a different way. I bet you've all seen something like this. This is a view of a rainbow. And that's sunlight, and it's been broken apart by water droplets in the Earth's atmosphere, and it takes that sunlight and turns it into the colors that make up sunlight. So you see all the colors of the rainbow. Well, it turns out scientists do that too. They take starlight and they spread it apart into the colors that make it up, and we call that the star's spectrum. So here you're seeing kind of a cartoon of the sun's spectrum. We took sunlight, spread it into the colors that make it up, and one of the things you notice about this sunlight is that it has dark lines in it. And the dark lines are caused by atoms in the sun's atmosphere absorbing sunlight. So let's talk a little about how that works. We've got the sun spectrum here, and the sun is mostly made of hydrogen. I know Joe told you that. The sun is mostly made of hydrogen, and you can see a few lines in the sun spectrum here that are caused by hydrogen. They're listed, they're marked with the letter H for hydrogen. Well, here is a cartoon of one of the ways, let's put it back. One of the ways of thinking about a hydrogen atom. A hydrogen atom has a proton in its center and one electron that's, you can say, in orbit around the proton. So in this cartoon, in this model of a hydrogen atom, the electron has different levels that it is allowed to be at. So it could be at that level 1 where it's a low energy level, or level 2 or level 3 or even higher levels. And in order to get the electron to go to those higher levels, one needs to add energy. Well, what's a good way to add energy to an electron in a hydrogen atom? Let's put it on the surface of the sun. And that gives the electron a lot of energy. It goes up to those higher levels. And as it does that, it soaks up that energy, and it soaks up only specific amounts of energy. One of those amounts of energy moves it from level 2 to level 3. And that is the amount of energy that corresponds to red light in the sun spectrum. So what you see is that energy is being soaked up by the hydrogen atoms, and you see a dark line in the sun spectrum. Well, we want to learn what the hydrogen is doing on the sun, and after the energy has been soaked up by the electron, then the electron relaxes down to a lower energy level, because we all like to be at lower energy levels, right? So the electron relaxes down to a lower energy level, and as it does that, it gives off light of those exact wavelengths. So here our electron's going to go from level 3 down to level 2, and doing that, it gives off the red color of light. So if we observe that red color of light, we can see what the hydrogens are doing, what the hydrogen atoms are doing on the sun. So let's go back to our view of the sun, looking at the visible light of the sun. We're looking at all the wavelengths of light that your eye could see. But if we only look at one wavelength of light that comes from hydrogen, we get a view that doesn't look so much like this. It looks more like this. Now, this is still in black and white. If we had a color camera on this, we would see that it's a beautiful shade of red colored light. And I also want to tell you that this is a double image. So a double exposure. It takes one exposure to get the disk of the sun and one exposure level to get the stuff around the edge of the disk. And Joe will show you that when we get to viewing the sun live. We call this view hydrogen alpha. That's the name of that one electron transition from level 3 to level 2. And we can see the sun in a different way. So that's a great way to learn more about the sun. What we're going to do now is go back to Joe, and he's going to show us the sun live and show us the hydrogen on the sun.
Okay, thank you, Judy, for that great information there. So, okay, let's go ahead and bring up our view of the sun in hydrogen alpha light. And this again will be a wide angle view of the sun here. Okay, here we go. Okay, hydrogen alpha light right here. Now the sun, it does rotate on its axis. Different parts of the sun rotate at different speeds. The equator rotates faster than the poles. Now, it'll take the sun about a month or so to rotate on its axis. And the sun has a powerful magnetic field. And as it rotates, these magnetic field lines, they get twisted up. And the areas where they twist up is where we have activity that happens on the sun. And we don't see much activity happening on the sun right now at this scale in hydrogen alpha light. But what I'll do here in just a minute is switch to our main telescope for a close-up view of the sun in hydrogen alpha light. Also, we don't see any sunspots right now, many sunspots. When you see a sunspot, they appear dark because they're cooler than the rest of the sun. And I use cool as a relative term. Temperatures of sunspots average about 6,000 degrees Fahrenheit or so. But let's go ahead and we will go to, I'm going to go ahead and put this on the big screen here. And let's go ahead and we'll switch over to our main telescope, also in hydrogen alpha light. And you will get to see what goes on behind the curtain while I do that. So give me 1 minute here. Okay, let me turn the brightness down here on that. Okay, so this is a view of the sun in a close-up view of the sun in hydrogen alpha light right here. And I will move the telescope and we'll take a look at an area of the sun that we call the limb, not the edge, of the limb of the sun. And let me make a camera adjustment. There we go. Now this fuzzy area that you notice on the sun, that is called the spicule layer. These are towering jets of gas, about half or so the size of the Earth here. Now let me move the telescope around and see if we have anything happening on the sun today. What I'm looking for is what is called a solar prominence. So we're going to take a trip around the sun today. See if anything's happening. Nothing yet. There should be something visible. When I was checking things out yesterday, there was an oh, here we go. Here's something. Hold on. Let's make a camera adjustment. So kind of toward the center of your screen. Oh, here we go. Wow, here we go. Great. But we see right here, those are known as solar prominences. Solar prominences. Now, when you see a solar prominence, they have kind of a looping effect because they're following the sun's magnetic field, the magnetic lines of force on the sun. Now, the prominences we can see today on the sun, those are extend maybe 3 or 4 times the size of the Earth. In fact, that brings me to the answer to the question that I posed earlier. How many Earths would fit inside of the sun? The answer is about 1.3 million. 1.3 million Earths should fit inside of the sun. If you got that answer right, give yourself a gold star, or if you were close to the right answer. Okay, back to our full screen view of the sun. And we'll continue our trip here around the sun. Let's do something here. Let's do this. There we go. Flying around the sun today. And we're going to change this too. And this is again with our main telescope, our 6-inch or 152 millimeter refractor telescope. Oh, here's another prominence. Take a look at that. As you can see my arrow here, that's a nice prominence there. Very good. Anything else happening? I don't see much else happening. I would say if you see something, give me a yell, but I can't hear you, so. Let's go back to the kind of 2-for-1 special on prominences we have today. Move that over here. Here we go, 2-for-1 prominences right here. One thing I want to mention too is you'll notice the image of the sun looks like it's kind of shimmering and moving. That's mainly because of distorting effects in the Earth's atmosphere. Standing on the Earth, looking at the sun or anything else in the sky is similar to standing in a parking lot on a hot summer day and you see the heat waves rising up. This is why telescopes, like the Hubble telescope, are so great, is because they're away from distorting effects of the atmosphere of the Earth. Now, I'm sure you've heard the poem, Twinkle, Twinkle, Little Star. Our technical term for twinkling is called scintillation. So I guess if you want to be more accurate, you could say, scintillate, scintillate, ball of gas. A little less poetic, but more accurate, the twinkle, twinkle, little star. Okay, let's see if we have, what kind of questions we have here in the chat. Judy, let's see here.
So one of the questions that we got was, where do all the different colors come from? You mentioned hydrogen, and I mentioned hydrogen, and we looked at that slide that showed the sun spectrum, and it looked like a rainbow with dark lines in it. The colors, the overall rainbow is what we call black body radiation. Everything that has a temperature is giving off radiation and giving off light, and the sun gives off light in what we call a continuous spectrum. It continues all the way from red through red, orange, yellow, green, blue, indigo, violet, all the way through the rainbow. And where that spectrum is the brightest depends on the temperature of the star. So the sun peaks kind of in the middle of the spectrum because it's kind of a medium star. Brighter, hotter stars are brighter in the blue end of the spectrum. Cooler stars are brighter in the red end of the spectrum. But all the colors come from that black body radiation. And we do see evidence of the elements that are present in the sun's atmosphere, and other elements absorb different wavelengths of light, but those show up as those dark lines. I hope that answered the question. Are there other questions?
Yes, I see one from, it looks like, let's see here, we have Vivian Messias, if I could pronounce that right. What is the difference between the sun prominences compared to the flares? Flares are caused by material welling up from the side of the sun, being disrupted by the magnetic fields. And the flares, they're much hotter. They are much hotter. Prominences are, you have cool hydrogen being suspended in what we call the chromosphere of the sun. So that's the main difference in between those. In fact, I can show you a video of a solar prominence or a solar filament if you would like me to do that. I do have a video that I can show you of a solar prominence. 1 second here, and let me show you that and get that video fired up here. One moment here, just a second. Of the solar filaments.
While you're doing that, can you answer this question? Does the sun grow larger every year?
No, the sun does not. The sun does not grow larger every year.
Here's another question, and it is: does each star have a different fingerprint or a rainbow color printout? And the answer is yes. That's how astronomers learn about stars. We learn lots about stars by taking the spectrum of the starlight and learning about that. Okay, so Joe wants to show us this beautiful image.
Yes.
Go ahead, Joe.
Yeah, here we have what this is a video of a solar filament. Now, the solar filaments, they appear dark because they're cooler than the rest of the sun. And when you see a solar filament, when you see a solar prominence on the limb of the sun, like we saw in our live view of the sun, this is a video of one taken from here that extends about 100,000 miles away from the limb of the sun. That prominence taken from here. This is not a live view. That is a recording.
So Joe, we also got a question from Alexandra Collins. What causes prominence? Is it a result of energy balance and Coriolis forces? And is it that?
Actually, it's more. Go ahead. Sorry, Judy. No, it's actually more to do with the sun's magnetic field. Because again, as the sun is rotating on its axis, these magnetic field lines, they get twisted up. And the areas where they twist up is where we have, sunspots, solar flares, and other activity happening on the sun.
Mm-hmm. Very good. Well, I see one that's a really interesting question. So I'm going to pop this up from Joe Alberti. Please explain why the sun rotates at different speeds at different latitudes. Do you know why that is?
Mainly it's because the sun is not a solid object. The sun is gaseous. We call this differential rotation. In fact, the planets Jupiter and Saturn, they do the same thing. You have different parts of them rotating at different speeds. Now, the Earth is a solid object, so it does not do that.
Yeah. Okay, I'm looking for more questions. And there's lots. Thank you so much for the questions. Was the video of the solar prominence sped up, or was it real time?
That is actually sped up over a period of several hours or so.
Okay. We're being asked again, what's the difference between solar prominences and solar flares? Joe, do you have a video of a solar flare that you can show us?
Actually, I do have a solar flare video.
I thought so.
Yes, I do have one. Notice the flares are brighter because they're hotter. And that's again because you have hot material welling up from inside the sun being disrupted by these powerful magnetic fields.
Yeah, I like to think of solar prominence as sort of more like the clouds that are in our sky on a regular day. And solar flares more like a storm.
That's another good way to think of it, Judy.
Yeah. Okay, here's one. Here's a comment. I read for some reason I read somewhere that if for some reason the sun suddenly disappears, it will take 7 minutes for us to see it. Is that true?
Well, the sun, I mentioned earlier the distance of the sun from the Earth are roughly about 93 million miles or 150 million kilometers. So we could also say the sun is about 8.5 light minutes away, because of the speed of light. So if something strange would happen, you wouldn't in 8.5 minutes, because of the speed. It would take 8.5 minutes for us to notice that. Mm-hmm. But it's unlikely that would happen. I would not lose any sleep over thinking about something like that could happen.
Okay, here's a question I want to take, and that is the sun part of the Milky Way? And the answer is, yes, it is. The sun is part of the Milky Way. Most of what we see at night in the nighttime sky, almost everything, is part of the Milky Way. Yeah, the Milky Way is our galaxy. So it's the city of stars that the sun and some 100 billion stars live. I got that number wrong, with us. And it's part of the Milky Way. How about this one, Joe? You ready for this one?
Oh, why not?
Can we predict when the sun will explode?
Can we predict when the sun will explode? Good question. Well, the sun, right now, it's about halfway through its life cycle. Now, the sun is not going to blow up in a supernova. What will happen when the sun exhausts its fuel, it will expand into what we call a red giant star. And eventually, it will poof off its outer atmosphere and form what is called a planetary nebula. And that's something that you can learn about more. You can learn more about in an upcoming program.
Okay, you want some more questions?
Let's see. Why don't we go ahead and go on to the next topic,
Okay.
Solar eclipses. But we'll have another question and answer session later on during the program. So Judy has a couple more things to share with you while I set up for this next part of the program, which will be about solar eclipses. So Judy, take it away for a minute.
Thank you, Joe. So, like I said before, I'm part of the K-12 education team here at McDonald Observatory, and I am sitting in the kind of an older telescope dome that's down here at our old visitor center end of the complex, kind of right next door to the roll-off building where Joe's telescopes, the telescopes we've been using, are. And these are telescopes right behind me that we use when we connect with student groups. So I have had the fun in the past couple of weeks of connecting with a whole lot of elementary students, showing them live views of the sun, much like what we did with Joe just now, only with these telescopes that are right behind me. And I'm sitting out here in this dome. I really thought it would be warmer today. I keep adding layers, but it is chilly and it is windy. And here we are looking at telescopes, and that's very fun. But we like to work with school groups. And so I'm going to talk about what we do with school groups. In the past, we've had students groups, classes usually, sometimes a whole school come and visit us. We also do teacher professional development here. We welcome homeschool families, and you can learn more about our education outreach program at McDonaldObservatory.org at the Learn tab. So I want to tell you what these students are doing. They came to visit us quite a few years back now, and they observed the sun, and they observed the sun sun in a safe way. What you're seeing here is these three girls are using a small telescope called an astroscan. Sunlight is going into the top of the telescope, and instead of them looking through the telescope with their eye, that would be really, really dangerous for their eyes. They are allowing the sunlight to exit through the eyepiece, and they're catching an image of the sun on a clipboard there. So those three girls are looking at an image of the sun in a safe way as they visit us here at McDonald Observatory. And I'm really hoping more of you can visit us or interact with us online in one of our web-based programs sometime soon. That would be great. Are you ready for the next thing, Joe? I'm ready to go back to you.
Yes, I'm ready. So the next topic, our final topic for the day, will be about solar eclipses. So let me get those slides fired up here for you. Here we go. Go to the big screen. Okay, solar eclipses. Here in this diagram, we can see what happens during a solar eclipse. We have the moon in between the Earth and the sun. Now, the reason we do not see a solar eclipse every month is because the moon's orbital plane is slightly tilted with respect to the ecliptic plane. So the moon does not always pass directly between the Earth and the sun. Sometimes the moon's shadow is too high, completely missing the Earth. Other times, too low, again, completely missing the Earth. But when things are just right, we have a solar eclipse. And there are different types of eclipses. First off, we have what is called a partial eclipse of the sun. The moon just, partially covers up the sun. Next, we have what is called an annular eclipse. The word annular comes from a Latin word annulus, meaning ring. Now, an annular eclipse occurs when the apparent size of the moon is not quite large enough to cover up the disk of the sun. This is sometimes poetically referred to as a ring of fire when you see one of those. Finally, we have what is called a total solar eclipse. During a total solar eclipse, we can see the sun's outer atmosphere, also known as the corona. Now, the last total solar eclipse visible from the continental U.S. was on August the 21st of 2017. Here's an animation of that eclipse. If you saw that eclipse, I might write that in the chat. I observed this eclipse, first one I'd ever seen, a very spectacular sight. I was observing it from southern Illinois. And here are some more pictures of the eclipse. In the top row, we can see the progression of the eclipse from the partial phase through the total phase to where you can see the corona, then to the end of the eclipse. The bottom picture shows you another safe way to view the sun by projecting its image onto a piece of white paper using holes in a cracker. And you can consume your solar equipment afterwards. Now, if you missed that one, you'll have another chance coming up here in a few years. We have one coming up on April the 8th of 2024. You can see the path it will take here across the country. We will have a ringside seat for this eclipse here in Texas. In fact, if you live in the Dallas, the Austin, San Antonio area, happens pretty much in your backyard. So start making plans now for this eclipse coming up on April the 8th of 2024. Now, if you missed that one, you'll have to wait a bit longer. There is a good one coming up on August 12th of 2045. I hope to be able to see that one too. Now, there are some coming up later in the century that might be well placed for younger viewers in the audience. Now, if you don't want to wait around to see one, you can travel when it's safe to do so. Here is a map that shows you annular and total eclipses happening over the next 20 years or so. We have a number of them happening all over the world, and you can do that whenever it is safe to travel. Okay, so that's some information about what causes eclipses, when and where you can see them, and another safe way to view solar eclipses. Okay, do we have any more questions? I'm sure we have lots of questions here. Let's see what we have here in the chat.
Joe, one of the questions that came in a while back was one from Dodie Stillman that said, Joe, what causes you to lose sleep as you ponder?
What causes me to lose sleep as I ponder?
Yeah.
Many things, I guess. I mean, many things going on in the world right now. That's kind of a tough question to answer, I guess. There are many things, so.
Yeah. Lots of things, but Dodie didn't ask me. But what causes me to lose sleep, I'm not worried about the sun running out of fuel or exploding or anything like that.
Definitely not. Definitely not.
My worries are mostly local. Like, what do I have to do tomorrow? That kind of thing. There were questions earlier about northern lights. Can you talk to us some about northern lights?
Yes, I can. Yes, I can do that. Northern lights, also known as the Aurora Borealis, and if you live in the southern hemisphere, they'd be called the Aurora Australis. Those are caused by particles from the sun that impact what we call the magnetosphere of the Earth. And these charged particles, or the Earth's magnetosphere, acts like a funnels these particles toward the poles of the Earth. That is why you see them more often. That's why you see them at higher latitudes. In fact, if you give me a minute, I can show you a picture of some of the northern lights. Let me remove my face here for a minute, and I will show you some pictures of the northern lights. I have some in my slideshow queued up just in case.
I saw that there was a really good bright northern lights show just last night or the night before, seen from Norway.
Here we go.
Wow.
Yeah, that's a picture of northern lights here. In fact, here's how they look from space. That's a picture taken from the International Space Station. So the astronauts on the ISS, they get a bird's eye view of the northern lights, or the southern lights.
Yeah. Well, I see a question in the chat that I really like. And it was answered in the chat, but I still want to talk about it. And that is the sun revolving around anything? We know the Earth revolves around the sun, but is the sun revolving around anything? The answer was answered in the chat. The sun is orbiting the center of the galaxy. So the center of the galaxy is a huge, huge, huge collection of stars. It's got a lot of mass, and so the sun orbits that just like the Earth orbits the sun. How about this one? This is for you, Joe. I saw Star Trek Discovery fly through a sun. How'd they do that?
How did they do that? It was magic.
The magic of Hollywood.
Magic. Yeah, I actually am a very big Star Trek fan. Other than astronomy, I kind of have a pretty good knowledge of Star Trek stuff. So, yeah, but current technology, we could not do that. But maybe someday.
I think they had their shields up. I think they had their shields up for that.
Had their shields up, right.
Yeah. How long does it take this? Oh, yeah, right. How long does it take the sun to orbit the center of the galaxy?
How long does it take the sun to orbit the center of the galaxy? Roughly 250 million years. In fact, the sun and the solar system, we're nowhere near the center of the Milky Way galaxy. If you think of the Milky Way galaxy as a big pizza, the core of the galaxy could be a meatball sitting at the center of the pizza. We might be maybe, perhaps an olive, kind of about 2/3 away from the core or the meatball of the galaxy. So we're kind of in the suburbs of the Milky Way galaxy.
And I see the moderators got there just as we did.
Okay.
They're on the ball. Do you know if that picture from the space station took any extra adjustment, or was it just how you see it when you're on the space station? Have you been up there? Do you know?
I've never been to the space station. I would go if I got a chance. I'm sure they did some adjustments on it.
Okay. Very good. All right.
I see a question here from Robert, if I pronounce this right, Ludeke.
This one?
How big is the black hole in the Milky Way galaxy? I was looking, I believe it is about 14 million times the mass of the sun or so. The sun has a mass of 330,000 times the mass of the Earth. Let me check that here, and let me check something real quick here. And four and a half million times the mass of the sun. It's called Sagittarius A.
So physically, how big would it be?
Physically, how big would a black hole be? Black holes, they're kind of a funny thing. I'm not an expert on those, but I can tell you one thing. Some types of sun stars will collapse into what is called a neutron star. A neutron star would be about the size of maybe a small city. So, a black hole could possibly be, microscopic maybe, or perhaps maybe the size of a beach ball. But they'd be measured more by their mass than more their actual size. Anything to add to that, Judy?
No.
No, okay. In fact, whenever we have our talk, whenever we do our virtual tour of the HET, there might be an expert that could tell you more about black holes, more than myself or Judy.
Okay, here's a question that I can answer. And the question is, why is the sun magnetic? And the sun is magnetic because a magnetic field is formed if you move an electric charge through space. Most of the hydrogen in the sun is what we call ionized, which means the electron has been lost from the proton. And so you have an electron and a proton. They're separate from each other. The sun is spinning, and so those charges are moving through space, and that generates magnetic fields. There's other motions of the gases in the sun, so the sun has quite a large magnetic field. Do you have anything to add to that, Joe?
That sounds pretty good. I see a question that popped up in the chat here. Let's see if I can get this to show up here.
There you go.
It says, Christina, she's 10. She's asking, how big is the sun compared to other stars? Well, Christina, the sun, it is kind of an average-sized star. And there are stars much bigger than the sun. there are also stars much smaller than the sun. One of the largest stars known is a star called Betelgeuse, in the constellation of Orion the Hunter. If Betelgeuse were placed in the sun's place in our solar system, it would extend out beyond the orbit of the planet Mars. But don't say Betelgeuse more than 2 times. And the smaller stars are called red dwarf stars. A red dwarf star may be about 1/10 the size of the sun, the diameter of the sun. So there are many, larger stars in the sun and many smaller stars in the sun.
Do you have time for one more?
Sure, fire away.
You spoke about how much heavier the sun is compared to the Earth. How do you know how much the sun weighs?
Good question. How do we know how much the sun weighs? We can calculate the mass of the sun and things by using various mathematical formulas. We can know the radius of the sun, also know its composition. Its composition by using the technique Judy talked about, known as a spectroscopy. And by using that, we can get a rough idea about the mass or so of the sun. Anything to add to that, Judy?
I think physicists you can calculate the mass of something, and I'm not a physicist, so.
Right.
But if you know how one thing moves in relation to another, there was another question about if the sun has gravity, and the sun does have, everything with mass has gravity. So everything made of atoms has gravity, and the mass of the sun affects the Earth. So if we know the mass of the Earth, then we know, and the orbital properties, Kevin is answering the question for us, then we can calculate back and get the mass of the sun. So it's all in the physicist. Thank you, Kevin, our physicist, for answering that question.
For helping us out. Right, yeah.
That question about, oh, go ahead.
No, I was going to say, you mentioned the mass of the sun. I mentioned you mentioned the mass of the sun. The sun's 330,000 times more massive than the Earth. If you weighed 100 pounds on the Earth, you'd weigh almost 3 tons on the sun.
Mm-hmm. Now, there was a question a ways back about the giant sun painting behind you, and yes, I painted that. It is in scale. It's 54.5 inches across, and it's what's along the equator of the sun in that picture are 1/2-inch blue dots. And to scale, a 1/2-inch blue dot is the size of the Earth relative to the size of the sun. So, anything else?
No, I think we're about to wrap things up today. Okay.
I think so too.
Well, we hope that you enjoyed our program today. Thank you, Judy, for your help today. And also thank you to the moderators helping out today in the chat. Now, tomorrow night, we're going to be having a Deep Sky program hosted by Stephen Hummel. He is a very accomplished astrophotographer, another colleague. In fact, he's my neighbor. He will be using telescopes that we have here at the observatory to view objects such as star clusters, nebulae, galaxies, many things we can see with our telescopes. That program will start at 10 o'clock tomorrow evening, last about an hour. Also, a shout out to Kevin, who's been in the background in case we have any technical issues today. Didn't have any major issues today. Also, a big thank you to the rest of the Visitor Center staff and our staff in Austin for making this program possible. Okay, so Judy and I would like to wish you a very good day. Thank you for joining us, and good day and clear skies. Thank you very much.
Thank you.
Bye-bye.
Bye.